In this video, I'll describe an assembly program to multiply two numbers. I will use a serial connection to a computer architecture on an Altera FPGA board. There are 25 instructions, 18 ordinary instructions, 3 directives, and 4 for the sequencer to adjust data flow. Multiply.s is the main program. The mathematical procedures are mult and div. I included several procedures for input and output. Put word, put line, get line, ASCII to word, and word to ASCII. A programmer can include these procedures directly in a program as macros using a .include directive, but there is a stack to effectively manage registers in memory. Stack procedures make procedure calls easy by automatically storing and restoring registers 1 through 10 for a procedure call. Multiply.s sends two prompts to a UART device and translates the response into decimal numbers. It multiplies those numbers and sends the response to the UART device. An emulator shows how multiply.s behaves. Here is an example of multiply.s running on hardware from a new hardware build to a multiplication result. A simple computer should start with the clock hold signal enabled. A programmer can assemble a memory initialization file using an assembler or an emulator. There are several assembly options listed in the Principles of Operations manual. Once assembled, a programmer can initialize SRAM memory and disable the clock hold signal. Multiply.s immediately sends a prompt to the UART device, which is visible on a TTY device for a connected PC. Simple computer stack procedures automatically manage registers for assembly programmers. A programmer can include call.s to invoke a procedure. Call.s will save registers 1 through 10, invoke the programmer's procedure, and then restore the saved register. Register 15 is a stack pointer address. Register 9 is a procedure address for call.s. Registers 11 and 12 are procedure arguments, and register 0 is a return value. The LCache, low cache, is the first instruction of multiply.s. It caches 1 in the low 8 bits of register 15 to initialize the stack pointer. The stack will start at address 0001 and grow to higher odd-numbered addresses. A simple computer sequencer uses a special control signal to read an instruction from memory. The sequencer and functional units wait for opposite clock edges. It writes that instruction to the first empty cache slot. It determines the appropriate control signal for each unit by 1. Comparing current hardware use to required hardware reservations for each instruction cache slot, and 2. Selecting the control signal for each instruction, and 3. Selecting the correct part of the control signal for each instruction stage. After the sequencer has selected the appropriate control signals for functional units and pipeline registers, the functional unit processes can assert whatever signals they need to assert. Hexadecimal value 3000 enables Unit 1, enables write for the program counter, and selects PC plus 2 as the input signal. Hex 2000 enables a pipeline register write for the instruction register. Hex 2000 for the pipeline enables a pipeline register write for the instruction register. Hex 9300 enables Unit 2, selects the appropriate control signals for instruction register and register file data input, and enables a register write. Control signal is reduced to a sparse Boolean matrix. Each instruction has a maximum of 5 stages. An instruction finite state machine may restart before the 5th stage if the instruction is complete. A visualization of those signals shows data flowing left from memory to a cache right through a pipeline. Starting at Unit 1, Unit 1 asserts new values for the program counter and the pipeline. The sequencer deallocates Unit 1 and enables Unit 2. Unit 2 asserts signals to write the register file based on control signals from the sequencer. The sequencer deallocates Unit 2. With functional communication on a serial interface, it's fairly easy to program new communication protocols. In this example, a hardware device broadcasts the hex value AB and listens for a second device to respond with the same message. The emulator responds with hex value AB, and the hardware program terminates. The sequencer also supports instruction-level parallelism. It may load up to 3 instructions into an instruction cache and run them simultaneously using the same hardware. This demonstration shows that when an ALU operation is delayed, it's possible for a programmer to schedule independent instructions.